Hello everyone, am I audible? Okay, so today we will start memory management and quickly I will explain memory management and then we will start solving the previous year questions. Okay, so today I will be explaining just the small part that today I will be explaining the basic concept behind the memory management. तो हमारे पास में दो ऑप्शंस हैं. Either what we can do is I will explain the theory and you will solve the questions, or what we can do is as I told you that you should study the topics first and then I will solve the question. If you have studied the theory of memory management, then I will solve the questions directly and you can study theory by yourself. So which approach you would like me to follow? You want me to explain memory management completely and then questions, or you directly want to solve the questions of memory management? Okay, how many people are there in the class who does not know anything about memory management? How many people are there in the class who does not know about the memory management? If you do not know anything about memory management, then you will not be able to understand the questions. Okay, if you are not able to understand the questions, you will not be able to touch them. Okay, अगर आपको टॉपिक ही नहीं पता है, आपको नहीं पता है, तो फिर आप डायरेक्टली क्वेश्चन सॉल्व नहीं कर पाओगे. Solve the questions please. Okay. So I will just go with the questions. Pranita, Nidhi, Prerna, Nidhi, that you do not know anything about memory management. Okay, so let us start solving the questions. If you are not able to solve the question, then we will come back to theoretical part. Right. So for example, the first question is on little theory and then questions. Oh my god. So it is feasible that I will explain the theoretical part quickly and then I will come to the questions. Yes, today this is the last session for today's class and tomorrow will be the same timings. Okay, when we talk about memory management, we are talking about how to manage the memory. Okay, how to manage the memory. Memory management means that we have very simple concept. The concept is that we have a process and we have to load this process into the main memory. Okay, we have a main memory in which we have to load this process. Okay, and this main memory may be divided into partitions or may not be divided into partitions. Right, let us say the size of the main memory is 1 megabyte and there is a process. The process demands, let us say, 20 kilobytes. The first you try to understand the problem क्या है. Problem ये है कि आपको एक process load करनी है into the memory and there will be some size of the process. Let us say process का जो size है वो 20 kilobytes है. That means process is saying that I want 20 kilobytes into the main memory. Okay, this is the question, this is the problem here. The solution for this is, there are two solutions and those solutions are, either we can provide the memory contiguously or we can provide the memory non-contiguously. Okay, when we say contiguous means that this 20 kilobytes into the memory will be provided sequentially. That means all 20 kilobytes will be provided sequentially. Okay, that means one byte after another. When we talk about non-contiguous allocation, in non-contiguous allocation we will divide the process into different partitions. For example, let us say the size of one partition is 2 kilobytes, so this process will be divided into 10 partitions. Okay, and these 10 partitions of this process may reside at the different places. We can give one partition here, other partition may be here and some partitions can be here. Okay, so there are two kind of memory management techniques, that is contiguous memory management and non-contiguous memory management, right? Let us understand what is the meaning of contiguous storage allocation and non-contiguous storage allocation. So in contiguous storage allocation, we have some techniques like static allocation and dynamic allocation, or you can say static partitioning or dynamic partitioning. Okay, so the first one is contiguous allocation. In contiguous allocation, we have two kind of strategies: single partition allocation scheme and multiple partition allocation scheme. Okay, so single partition means that what we will do in single partition, there will be only one partition of the memory. Okay, there will be only one partition of the memory, and you know that already in the memory you will have the operating system. Okay, you will have operating system in the upper space of the memory, and rest of the size will be for user. Now user can load the processes into the user space. Whenever user will create any process, user will load the process into the user space. Let us say the size of memory is 1 megabyte. Then let us say some 40 kilobytes are given to operating system, and some, let us say, remaining is given to user partition. So in single partition allocation scheme, we will have only one partition, and we know that we can load only one process in one partition. That means the problem with the single partition allocation scheme is that you can load only one process because you have only one partition, right? Because you have only one partition, that's why you can load only one process. Then we have multiple partitioning scheme. In multiple partitioning scheme, we have two more techniques, that is called as fixed size partitioning and dynamic size partitioning. Fixed size partitioning simply means that so I told you about single partitioning scheme. In this you will have only one user partition. Okay, this is user partition, and this is for operating system and interrupt vectors. And one will be for operating system, one partition for operating system and one partition for user. So not many decision to make. That means अगर कोई भी process आएगी, let us say any process comes, that process will be given the partition, this partition. Okay, so user process will run in the user space. Then any other process P1 comes, that process will replace this process P0, right? Because we have one partition, and in one partition we can only load one process, right? So the disadvantage of this single partitioning scheme is that you can load only one process into the main memory, right? Then you have static partitioning. Static partitioning can be unequal size partitioning or equal size partitioning. What you are doing is, for example, let us say you have 64 megabyte memory, the size of the memory is 64 megabytes. Okay, what you are doing is, when we are talking about fixed size partitioning, or you can say equal size partitioning, in equal size partitioning you are partitioning the memory into equal size partitions. All the size of all the partitions will be same. Let us say that is 8 megabytes. Yes, MS-DOS can be the example of the single partitioning scheme. Dynamic is also called as variable size partitioning. Yes, dynamic is called as variable size partitioning, that is right. Okay, so under static partitioning, what is the meaning of static partitioning? Static partitioning simply means that you have a memory, and before starting any process, you have simply divided the memory into the partitions. On the partitions can be equal size partition or unequal size partitions. So in this you have unequal size partitions, right? For example, the size of one partition is 2 megabytes, the size of one partition is 4 megabytes, the size of this partition is 6 megabytes. So you have unequal size partitions. So under static scheme we have two kind of partitioning scheme, that is equal size partitioning and unequal size partitioning. Obviously when any process will come, let us say you have a process, this process requires 6 megabytes. Okay, so in this you do not need to make any decision. Obviously if you have a process of 6 megabyte, you can put this process in any partition, right? You can put this process in this partition or in this partition, does not matter, because in this partition also 2 megabytes will be wasted, and in this partition also 2 megabyte will be wasted. That means there is no decision to make here. आप कहीं पर भी डाल दो उस प्रोसेस को, कोई फ़र्क नहीं पड़ेगा, क्योंकि हर एक पार्टीशन में इक्वल साइज का ही वेस्टेज होगा. अब सो पार्टीशन साइज इज 8 megabytes and the size of the process is 6 megabytes. So this complete partition will be given to this process. This process will use only 6 megabytes out of the 8 megabytes. Remaining 2 megabytes is called as internal fragmentation. Okay, when we have the wastage inside a partition, that is called as internal fragmentation. Right? So but in case of this unequal size partitioning, if let us say you have a process P0 with 6 megabytes, you have to decide in this you have to decide which partition you should give. So for example, this partition you cannot allocate because this is not enough, this is also not enough, you can allocate this partition. This process P0 will be allocated this partition, and process P0 will be stored in the memory in this partition, because in this partition there will not be any wastage, right? The size of the process is also 6 megabytes and the size of the partition is also 6 megabytes. This will completely fit. ओके ये बिल्कुल पूरा का पूरा फिट हो जाएगी प्रोसेस के अंदर. बट अगर आप इसको यहाँ पर अलोकेट करते हो, इफ़ यू अलोकेट द साइज हियर, then in this partition there will be a internal fragmentation of 2 megabytes. In this partition also there will be an internal fragmentation of 2 megabytes. In this partition you will have the internal fragmentation of 6 megabytes. In this partition the size of this partition is 16 megabytes, and in this partition there will be a wastage of 10 megabytes, right? So for that we use some algorithm that is called as first fit, worst fit and best fit. Okay, so according to first fit, wherever you will find the enough space you will put that process there. जहाँ पर भी आपको पहली बार में स्पेस मिल जाएगा, द इनफ स्पेस यू विल पुट देयर. बेस्ट फिट मीन्स दैट यू विल पुट द प्रोसेस ओनली इन दैट पार्टीशन वेयर देर विल बी लीस्ट वेस्टेज, जहाँ पर सबसे कम इंटरनल फ्रेगमेंटेशन होगा. फॉर एग्जाम्पल अकॉर्डिंग टू द वर्स्ट फिट, अकॉर्डिंग टू द बेस्ट फिट, दिस प्रोसेस विल बी allocated this partition. Okay, so obviously in the fixed size partitioning you do not need any algorithm, right? You do not need any algorithm in case of fixed size partitioning. Does not matter where you will store this process, this will always be 2 megabytes of wastage. So wherever you will have fixed size partitioning scheme, in that case there will be always internal fragmentation. For example, paging is fixed size partitioning scheme. In paging you will have internal fragmentation, and segmentation is unequal size partitioning. In that you will have external fragmentation. We will talk about what is internal fragmentation and external fragmentation. So this is static partitioning, right? So in fixed size partitioning the memory is uses inefficient. Okay, any program no matter how small occupies an entire partitions. Okay, so there will be like memory wastage will be too much in this. Let us say if we have a process P0, this requires only 2 megabytes. Okay, it does not matter wherever you will store this process, it will always waste 6 megabytes. Okay, one complete partition will be given to this process and only 2 megabytes will be used, right? So 6 megabytes will be wasted in all the partitions. So in case of fixed size partitioning there will be lots of internal fragmentation. In variable size partitioning you can put this process here and there will not be any internal fragmentation, right? Then in case of dynamic partitioning, static partitioning में आपने क्या किया? In the static partitioning आपने प्रोसेस स्टार्ट करने से पहले मेमोरी को पार्टीशन करके रख दिया. अब प्रोसेस आएगी और आप किसी पार्टीशन में उसको रख दोगे, right? In the dynamic partitioning you are just partitioning the memory just before the process comes. ऐसे ही है कि आपके पास में एक बहुत बड़ा लैंड था, आपने उस लैंड को एक बहुत बड़ा आपके पास में लैंड था, you have simply divided this land into multiple portions like this. ओके, विदाउट इवन व्हेन द प्रोसेस कम्स. ओके, अभी तक कोई बंदा इस लैंड में आपने इस लैंड को यू हैव डिवाइड दिस लैंड इनटू 4 पार्टीशंस एंड यू आर मेकिंग सम फ्लैट. ओके, आपने यहाँ पर एक फ्लैट बना दिया, आपने यहाँ पर एक फ्लैट बना दिया, आपने यहाँ पर एक फ्लैट बना दिया और आपने यहाँ पर एक फ्लैट बना दिया. अब एक बंदा आया, उसने कहा कि मुझे एक घर चाहिए. तो डज नॉट मैटर कि आप इसको कितना स्पेस चाहिए, इसको पूरा का पूरा घर मिलेगा, राइट? डज नॉट मैटर इसको कितना स्पेस चाहिए, आपको इसको पूरा का पूरा घर मिलेगा, राइट? बट इन केस ऑफ डायनामिक पार्टीशनिंग यू विल नॉट पार्टीशन अ प्रायर. ओके, आप पहले से ही पार्टीशन करके नहीं रखोगे. जब भी कोई प्रोसेस आएगी, जितना साइज उस प्रोसेस को चाहिए उतना आप पार्टीशन कर दोगे. पार्टीशंस आर ऑफ वेरिएबल लेंथ एंड नंबर्स. प्रोसेस इज allocated exactly as much memory as required. That means there will not be any internal fragmentation, right? There will not be any internal fragmentation because what we are doing in dynamic partitioning is, ओके, हम डायनेमिक पार्टीशनिंग में ये चीज़ कर रहे हैं. सो इन द डायनेमिक पार्टीशनिंग इनिशियली यू विल नॉट हैव एनी पार्टीशन इन द मेमोरी. इनिशियली मेमोरी विल बी अ सिंगल पार्टीशन. व्हेन एनी प्रोसेस कम्स, लेट अस से प्रोसेस P1 comes and process P1 requires 320 kilobytes. So what we will do is we will make a partition of 320 kilobytes out of this particular partition and we will allocate this to process P1. Now the user space is having 2 partitions. One partition allocated to process 1 and then other partition is empty. Then a new process comes, this process requires 224 kilobytes. Then out of this remaining portion you will make one more partition of 224 kilobytes and you will allocate that partition to process P2. That means जितना भी किसी लेटर से एक आपका पूरा फ्री स्पेस था, वहाँ पर एक बंदा आया, उसने कहा कि मुझे यहाँ पर फ्लैट बनाना है, तो आपने उसको इतनी ही ज़मीन दी जितनी उसको चाहिए थी, राइट? इन केस ऑफ स्टैटिक पार्टीशनिंग आपने पहले से ही ज़मीन के पार्टीशन करके रख दिए. अब कोई बंदा आएगा, उसको पूरी ज़मीन खरीदनी पड़ेगी, राइट. इसी तरह से यहाँ पर है, द प्रोसेस विल बी एलोकेटेड एग्जैक्टली the size they require. That means there will not be any internal fragmentation, right? Because you are allocating only exactly the size required. Then let us say any new process P3 comes. Okay, now you have this free space. Okay, you have this free space of 352 kilobytes. Let us say a new process comes with the demand of 288 kilobytes. A process P3 comes. So what you will do is, from this partition of 352 kilobytes, you will make two partitions. One partition will be of 288 kilobytes and remaining partition will be 64. So you will keep partitioning the memory according to the demand. Okay, in dynamic partitioning, the partitions will be at dynamic time, right? Partitions will be at the runtime. When the processes are coming, you are dividing the memory into partitions, right? In static partitioning, आपने पहले से ही partition करके रख दिए थे. Okay, so then you have 64 kilobyte partition. Now what happens is, let us say the process P2 completes the execution and it leaves the memory, right? When process is completes, it will simply release the memory. So ऐसा है कि एक बंदे ने घर लिया, उसके बाद में उसने उस घर को छोड़ दिया. अब होगा क्या, उसने उस लैंड में घर तो बना ही लिया था ना, उसने पार्टीशन तो बना ही लिया था. अब प्रोसेस हैज़ ऑलरेडी क्रिएटेड द पार्टीशन. नाउ व्हेन द प्रोसेस विल रिलीज दिस पार्टीशन, you will have a empty partition of 224 kilobyte. Let us say a new process P4 comes and it requires 128 kilobytes. So now you have two free partitions. One partition is this, one partition is this, right? In this you cannot allocate because the size of the process P4 is 128 kilobytes, right? So you will make one more partition from this partition and you will allocate this to process P4. Now you have free space of 96 kilobytes and 64 kilobytes, right? So like this, processes will keep releasing the partitions. For example, let us say now process P1 also completes. Process P1 completes and it will release the partition, this partition. Okay, now you will have one more free partition, that is 320 kilobytes. Let us say now again process P2 comes with a demand of 224 kilobytes. Then we cannot allocate here, we cannot allocate here. So we will make the two partitions of this partition and we'll allocate to process P2. Now you have three partitions left, that is 96 kilobytes, 96 kilobytes and 64 kilobytes, right? Let us assume that a new process comes with 128 kilobyte of demand. My question is, let us say process P5 comes and process P5 requires 128 kilobytes into the memory. Then what you will do? What you will do in this case? Obviously, do we have 128 kilobyte free space in memory? So yes, we have 96 kilobyte free plus 96 kilobyte free plus 64 kilobyte free, right? So you have 6 plus 4 10, 10 plus 4 16, 6 plus 9 15 plus 9 is 24. That means you have 256 kilobyte of memory free in the memory, but still you cannot allocate it. Right, you cannot allocate this memory to this process. You have enough memory, okay, you have enough memory available, but you cannot allocate this to memory to the process P5 because this space is not contiguous. Contiguous means it is not together, right? This space is not contiguous available. That's why this is called as external fragmentation. Okay, there will be an external fragmentation because when the required memory is available, but it is not contiguously available, that is called as external fragmentation. Okay, so as the students are saying that the solution for external fragmentation is compaction. Compaction means that just move all the occupied partition above and move the this empty partition here, then move this partition here and then move these partitions here. So that means all the occupied partition will go up and all the free partition will go down. That means all the partition will become together and then you can allocate it, right? So we have this question about the fragmentation, and this question is saying that the available main memory for loading process is 64 megabytes. Okay, you have a main memory of 64 megabytes which is divided into fixed number of partitions, each of 8 megabytes. Okay, so you have each partition of 8 megabytes. That means you have a memory like this in which you have 8 partitions. The size of the memory 64 megabytes, which is divided into 8 partitions of each 8 megabyte. Okay, each partition is of 8 megabytes like this. 3 4 5 6 7. You have this these partitions, 8 partitions, right? So you have 8 partitions in this memory. If the process are of size 6 megabyte and 4 megabytes, okay, you have processes and the size of the processes In static, why leftover space is not called external fragmentation? In static also there is external fragmentation. Okay, in static memory allocation, in the static partitioning also there will be some external fragmentation. For example, if you want to load a process, okay, you want to load a process of 18 megabytes. Okay, if you want to load a process of 18 megabytes, you cannot load this process into memory, right? You have enough memory available, but that is not in the form of partition, so there will be an external fragmentation. External fragmentation can also be in variable size partitioning. Okay, under static partitioning we also have variable size partitioning, so in this also external fragmentation is possible. The problem is that in static in the static partitioning you cannot use compaction, because compaction means you can move the memory locations up and down, and that can be only done when you have dynamic partitioning. In the static partitioning you cannot touch memory, right? You already have fixed the partitions. You cannot move free space and like occupied space above and below. So the compaction is only the solution for the dynamic partitioning, right? Not for static partitioning. The external fragmentation can be in static partitioning also, right? So this question is asking if you have the processes of 66 megabytes and 4 megabytes, then how much internal fragmentation will be there? So you can see you are using 16 megabytes. Okay, you are using 16 megabytes total you have used 16 megabytes, and out of that the partition is so the internal fragmentation is 2 megabyte internal fragmentation is there, and you can see 4 megabyte partition is 4 megabyte internal fragmentation is there. So out of the 16 megabytes, 6 megabyte is the internal fragmentation into 100. Okay, so this will be something, I think 37.5%, right? So internal fragmentation will be 37.5%. So we have in the dynamic storage problem, as I told you, we have three algorithms, that is called as first fit, best fit and worst fit. Okay, so in first fit allocate the first hole that is big enough. In best fit allocate the smallest hole that is available, that is enough. Okay, worst fit means allocate the largest hole. Okay, for example, if you have this memory, okay, in this memory you have the variable size partitioning. The size of this partition is 2 megabytes, the size of this partition is 4 megabytes, the size of this partition is 6 megabytes, and size of this partition is 8 megabytes, and let us say this is 10 megabytes. Let us say a new process comes P0, and P0 requires, let us say, 6 megabytes. Okay, process P0 requires 6 megabytes. Then according to the first fit, this partition will be allocated. Okay, आप क्या करोगे? You will start searching from the first partition. Wherever you will find the big enough partition, you will allocate that partition to the process P0. Okay, according to first fit. According to best fit, you will allocate that partition in which you will not have any internal fragmentation. So internal fragmentation means according to best fit, you will allocate also this space, because in this partition there will be zero internal fragmentation, right? According to worst fit says that you will allocate that partition in which you will have the largest number of internal fragmentation. जिस partition के अंदर सबसे ज़्यादा wastage होगा वहाँ पर आप allocate करोगे. First fit means that जहाँ पर भी आपको पहले free space मिल जाए वहीं पर डाल दो. Best fit means वहाँ पर डालो जहाँ पर internal fragmentation बिल्कुल कम होगा, बिल्कुल सबसे कम होगा. Worst fit means says that इसको आप वहाँ पर डालो जहाँ पर सबसे ज़्यादा इंटरनल फ्रेगमेंटेशन होगा. तो सबसे ज़्यादा इंटरनल फ्रेगमेंटेशन कहाँ पर होगा? यहाँ पर. सो अकॉर्डिंग टू वर्स्ट फिट दिस प्रोसेस विल बी लोकेटेड दिस स्पेस, राइट? सो दिस इज ऑल अबाउट फर्स्ट फिट, बेस्ट फिट एंड वर्स्ट फिट. देन वी हैव नॉन कॉन्टिग्यूअस मेमोरी एलोकेशन इन विच वी हैव पेजिंग, segmentation and paging with segmentation. So this is not in your syllabus, we will study only paging. Okay, we will see inverted paging and multi-level paging, right? So paging is nothing but paging is a equal size of partitioning. So Khushbu, next fit means that what you will do is you will check in the, so you will check first partition that is free, you will use the next partition. Okay, next partition, next fit means that you will start searching from that part where you have where you did put the last partition. Okay, अगर आपने पिछली प्रोसेस जो है वो यहाँ पर रखी थी तो अगली बार आप यहाँ से सर्चिंग स्टार्ट करोगे अकॉर्डिंग टू नेक्स्ट फिट. Why can't we use word external fragmentation here just because it is static partitioning? नो, एक्सटर्नल फ्रेगमेंटेशन का मतलब क्या है आप समझे नहीं हो. इंटरनल फ्रेगमेंटेशन इज डिफरेंट थिंग, एक्सटर्नल फ्रेगमेंटेशन इज डिफरेंट थिंग. इंटरनल फ्रेगमेंटेशन मीन्स दैट देर इज a wastage inside a partition. When there is a wastage inside a partition, that is called as internal fragmentation. External fragmentation means that अगर आपके पास में you have a memory, okay, for example you have this memory and you want to allocate up, you want a size of 9 megabytes. Okay, you have a process P1 which requires 9 megabytes. You cannot allocate 9 megabytes in this memory, so there will be an external fragmentation of 9 megabytes. Why? Because you have the enough space available, right? You have enough space available for this process, but still you cannot allocate it because that is not contiguously available, right? You have maximum contiguous available is 8 megabytes. That's why this is called as external fragmentation. Static and dynamic in both of these external fragmentation is possible. You have to concentrate only fixed size partitioning and variable size partitioning. If the partitioning is fixed size partitioning, there will be internal fragmentation. If the partitioning is variable size partitioning, then there will be external fragmentation. That's why in paging we have internal fragmentation, in segmentation we have external fragmentation, because paging is simply fixed size partitioning scheme, right? So in paging what we do is we will divide the process into the pages and we will divide the memory into the frames. So we have, yes, that is external fragmentation. When you said that you have the partition of 96 megabytes, okay, you have a partition of 96 megabytes and 96 megabytes here and 64 kilobytes here, right? So total available memory is 256 kilobytes. A process P5 comes, that process requires 128 kilobyte, but still this process cannot be allocated this space. हम इस process को ये space allocate नहीं कर सकते क्योंकि ये contiguously available नहीं है, मतलब एक साथ available नहीं है कहीं पर भी, right? कहीं पर भी ये एक साथ available नहीं है. आपके पास में इतना स्पेस तो अवेलेबल है मेमोरी के अंदर, बट वो कॉन्टिग्यूस नहीं है, एक साथ नहीं है, इसलिए वो एक्सटर्नल फ्रेगमेंटेशन हुआ. Yes, because of dynamic partitioning. So in paging what you will do is you will divide the memory. So physical address space, so physical address space simply means main memory. जहाँ पर भी physical address space लिखा हो that is means physical memory और main memory और primary memory, all these are the same thing, or RAM, right? So can be non-contiguous. Process is allocated this physical memory whenever the latter is available, right? So in paging you can allocate the space non-contiguously. For example, when we were talking about the contiguous allocation scheme, in this contiguous allocation scheme, that in this we are saying that if a process demands 1 megabytes, you have to allocate 1 megabyte contiguously. Okay, that means contiguously मतलब एक साथ आपको देना पड़ेगा पूरा 1 megabytes. According to non-contiguous technique, what you can do is you can divide this process into the partitions, into different kind of different size of partitions, and then you can allocate the partitions in different techniques. For example, I can allocate one partition of 64 kilobyte here, I can allocate one partition here, and I can allocate other partition at some other place, right? So that is non-contiguous allocation. In non-contiguous allocation we can allocate the memory non-contiguously, right? तो यहाँ पर ये आपके पास में you do not have this restriction that the memory should be given contiguously. Okay, so in memory what you will do is you will divide the virtual memory. Okay, virtual memory will be divided into pages and physical memory will be divided into frames, and the size of frame will be equal to size of pages. Okay, size of frame will be equal to size of pages. Right? So we will directly come to the questions of paging and segmentation, and I will explain the concept of this through the questions. So the first question is on first fit, best fit and worst fit. In this it is saying that you have a memory. Okay, in this memory you have some partitions. Okay, you have this memory. In this memory you have some partitions, then the size of partition is 100 kilobytes. Okay, so you have 100 kilobytes of partition, you have 500 kilobytes of partitions, then you have a 200 kilobyte partition, and then you have a 300 and 600 kilo partitions. Right, if we have processes needing memory 212 kilobytes, okay, we have a process, we have the memories of, we have a process of size, let us say process P0 requires 212 kilobytes, process P1 requires 417 kilobytes, process P2 requires 112 kilobytes, and process P3 requires 405 kilobytes. So which of the following memory allocation technique will be suitable to allocate the memory for all these processes? Okay, for example, I have to find out according to first fit, best fit, and worst fit. Okay, this is asking you which of the following memory allocation techniques will be suitable to allocate memory for all the processes. Okay, you have to allocate the memory to all the processes, right? If we use first fit, according to first fit, this process will be allocated which space, this process will be allocated this partition, right? Because this requires 212 kilobytes, right? This will require 212 kilobytes. Then P1 will be allocated 417 kilobytes, this requires 417 kilobytes. You will search which partition is enough for 1 to 417. So this process P1 will be given this partition, right? Then 112 kilobytes, this will be given this partition, because this requires 100 kilobytes, and this is the first partition which is free from the top to bottom. Then we have process P3. We will not be able to allocate the space to process P3 because we do not have any partition left which is of size 405, right? We do not, this, we have only two partition left, this partition and this partition, and then both of these partitions are not enough. Okay, these partitions are not enough for these processes. Then according to best, let's search for best fit. According to best fit, process P0 will be allocated this partition, because in this you will have the least internal fragmentation. Okay, यहाँ पर सबसे कम internal fragmentation होगा. For this process you have three options, this option, this option, and this option. Out of these three options, only this is having the less internal fragmentation. Then this process P1 will be given this partition. Okay, this partition will be given according to the best fit. Then 112 kilobytes, this process will be given this partition, right? Then 405 kilobytes, this will be given this partition. That means all the processes will be allocated the space. That means second one is, so this best fit algorithm is the best, right? According, if you will use best fit algorithm, all the processes will be given the partitions. Okay, next question is, consider a paging system with with the page table in memory. Each memory reference takes 200 nanoseconds. The TLB has the hit ratio of 75%, and the time to look for the pages in TLB is almost negligible. The effective time taken by a paged memory reference in nanosecond is what? So what happens is, the process is like this. Whenever CPU want to generate and whenever CPU want to access any data from the memory, CPU will generate a virtual address. Okay, and in case of paging, the virtual address is divided into page number and offset. P is called as page number and D is called offset. You will take this page number and first you will search in TLB. TLB is nothing but a small cache memory. Okay, it is a cache memory which can hold a very small amount of page table. In TLB we will store the page table, not the complete page table, but a very small portion of the page table, right? So if you do not know what is page table, then you are in the wrong course. You should join the complete course. If you do not know what is page table, then it's not my fault, right? Then you should have enrolled in the complete course, because I am expecting that at least if you are coming in the crash course, then you at least know what is the page table, right? So first you will search the page number into the TLB. Now in TLB there are two chances. Either in the TLB we can have a hit. If there is a hit in TLB, then the data will be sent to CPU. Okay, then the data will be sent to CPU. But if there is a miss in the TLB, then you will go to the main memory. Okay, in the main memory you will access page table. Okay, in the main memory you will access page table, and if the page is found in the main memory, then this will be converted to the physical address, right? If there is a hit in the cache memory, okay, if there is a hit in cache memory, right? If there is a hit in the cache memory, then you will get the physical address from the cache memory. And physical address is divided into two parts, that is frame number and offset. So you will take the frame number and offset and you will go to the main memory, okay, and you will access main memory from this frame number. Okay, so your page table will help you to find out the physical address, because the main memory is divided into frames and virtual memory is divided into pages. So CPU will generate the virtual address, that means CPU will generate the page number. You have to convert the page number into the frame number, and to convert page number into the frame number you will have a page table. Okay, page table is simply a table which will be used to convert the page number into the frame number. So these entries are telling you that that page number 0 is in the memory frame number 1, right? So if CPU generates page number 0, then you will have F3 here, that means page number 0 is in the frame number 1. So the formula for this will be, effective memory access time will be, first you will access TLB. Okay, so TLB hit will be given hit ratio of TLB into access time of TLB. Okay, if there is a hit in TLB, you will access TLB and then you will access main memory. Okay, this time is for virtual address translation, and this will be for memory access, right? Plus if there is a miss in TLB, okay, if there is a miss in TLB, then you will have to go to the main memory for the page table. You will access the page table for you will access main memory for the page table, then you will transfer that page table into the TLB, then you will access the data from the main memory. Okay, so to access data you have two steps. First you have to convert virtual address to physical address, then you will take that virtual address, that you will take that physical address और उससे फिर आप memory access करोगे. Remember यहाँ पर प्रॉब्लम क्या है? प्रॉब्लम ये है कि CPU जो है वो वर्चुअल एड्रेस जनरेट करता है. CPU ऑलवेज जनरेट द वर्चुअल एड्रेस एंड मेमोरी कैन ओनली बी एक्सेस्ड विद फिजिकल एड्रेस. Okay, so we require address conversion. We have a page table. What page table does is, page table will convert from virtual address to physical address. Okay, page table is stored in the memory management unit, and for memory management unit we use page table, right? So the formula will be this. In this everything is given. For example, in this question it is given that memory reference takes 200 nanoseconds. That means memory access time is given 200 nanoseconds, right? Hit ratio of TLB is given 0.75, right? And TLB access time is negligible. It is given that TLB access time is 0, negligible. So effective memory access time will be hit ratio of TLB, that is 0.75 into access time of TLB 0 and access time of memory is 200, plus 1 minus 0.75, that will be 0.25 into memory access time will be 400 nanoseconds. Okay, 200 plus 200 and plus 0. Solve this equation and you will get your answer. So this will be 150. Okay, so 200 into 0.75 will be 150, and this will be 400 into 0.25, that will be 100. That means you will get the answer 250 nanoseconds. So note down this formula anywhere. Okay, so this is the this is the paging with TLB. We have two formulas of effective memory access time. For effective memory access time we have two formulas. One formula without TLB. If you are not using TLB to store the page table, so without TLB the formula will be simply 2 times memory access in case of one level paging, because one memory access to convert virtual address to physical address and one memory access to finally access the data. And effective memory access time in case of if you have TLB, then the TLB hit ratio and the TLB access time will be given. The formula will become hit ratio of TLB into access time of TLB plus access time of main memory plus 1 minus hit ratio of TLB into access time of memory plus hit ratio plus access time of TLB plus access time of main memory. Okay, this will be the formula for one level one level paging with TLB. Okay, I will skip this question for now because this is on multi-level paging. So first we will solve the question on single level paging, then if we get the time we will solve the question of multi-level paging. Now look at this question. In this question it is given that the size of the virtual memory is the size of the virtual address is Okay, virtual address is given of 32 bits, right? And it is given that the size of the physical address is 28 bits, right? The main memory is byte addressable. The size of each page table entry is 32 bits. So size of page table entry is 32 bits. And the page size is given 8 kilobytes. Page size is 8 kilobytes. It is saying that the maximum number of bits that can be used for the protection and other information to keep in page table entry. So we know that we have a page table like this. In page table, what do we store? In page table, we will store the frame number, right? In page table, we store the frame number, and then we store the remaining information like valid invalid bit and protection bit or other bits, dirty bit, right? All these bits are stored. So these are the optional part. This is the mandatory entry into the page table. So in the page table, we have to find out the size of the page table. Then the size of the page table will be so first let us try to understand. It is saying that it is simply asking how many bits are left. Well, that means it is asking that how many bits are left to store the other information, right? So in this case, it is given that the page table entry size is 32 bits, right? This complete entry of the page table is of 32 bits. If you can find out how many bits are there in the frame number, then you can find out how many bits will be remaining, right? So we know that the physical address is divided into page number, physical address is divided into frame number and offset. Okay, so it is given that the physical address size is 28 bits, right? And you have divided into frame and offset. We can find out the offset bits from the page size, log base to page size. Okay, and the page size is given 8 kilobytes. You can say this will be log base to 2 to the power 13, right? 2 to the power 13 bytes. 8 kilobyte is nothing but 2 to the power 13 bytes. 8 means 2 to the power 3, k means 2 to the power 10. So you can say 2 to the power 13 bytes, right? So that means there will be 13 bits. Log base 2 to the power 13 will be 13. So that means D part will be of 13 bits and the remaining 15 bit will be for frame number. Okay, so we have successfully find out the frame number will be of 15 bits. So you have find out from here to here, this will be of 15 bits. Okay, so the remaining bits, that is 32 minus 15 will be 17 bits. So you can use 17 bits for the other information, right? Frame number will be of 15 bits. That means remaining bits are how many? So remaining bits are 17 because the size, so not 17, 13. Okay, because the physical address size is 28 bits. So remaining 15 bits are for frame number, right? So remaining 15 bits are for frame number, and then 17 bits will be left for the other information. So the answer will be 17. Okay, 17 bits. How we can find out the, so it is given that the virtual address is also given, and the virtual address is divided into page number and offset, right? And it is given that virtual address is of 32 bits. Okay, so offset part we have already calculated. Offset part is of 13 bits. Then remaining 19 bits will be for page number. Okay, so there are some formulas which you should remember in paging. Okay, there are some formulas in paging which you should remember and those formulas I will keep discussing during the questions. Okay, we will keep solving the questions and I will keep explaining them. So this is saying that our demand paging uses a TLB and single level page table stored in main memory. Okay, this is single level paging. The memory access time, it is given that the memory access time takes 5 microseconds and the page fault service time is, so it is given that page fault service time is 25 milliseconds. Okay, so it is saying that if 70% accesses are in TLB and the remaining 20% is not in present in memory. Okay, so it is saying that and of the remaining 20% is not present in main memory. So it is saying that total let us say we are making 100 accesses. Out of the 100 access will be in TLB and remaining 30% access will be in memory, and out of those 30 accesses 20% is not present in memory. Okay, so I hope you are getting this. This is saying that when we will make 100 access, out of those 100 access, okay, 70% access will be in TLB Okay, so 70% access will be in TLB and remaining 30% access will be in memory. Okay, remaining 30% access will be in memory. So there are two chances, right? Either page will be found in TLB or it will not be found in TLB. अगर पेज TLB के अंदर नहीं मिला तो आपको मेमोरी के अंदर मिलेगा. अब ये कह रहा है कि आउट ऑफ दोज 30% विच यू आर मेकिंग इन TLB in memory, they are not found in the memory, not present in memory. So it is asking what will be the effective memory access time in memory in milliseconds. So understand the process. What is the process here? CPU will generate a virtual address. Okay, CPU ने एक virtual address generate किया, page number and offset. Okay, you are taking this page number and you are going into the TLB. It is saying that out of the, let us say if you are making 100 accesses, 70% access are found. That means 70% there will be hit in TLB. Okay, there will be 70% hit in TLB because there is 30% miss. Because 30% miss, that means for the 30% remaining accesses you have to access the main memory, right? For the 70% access you will directly get the frame number and offset and you will access the main memory. This is the first situation. You will access the memory and you will access the data with the physical address. Second case is that if let us say if there is a TLB miss, okay, if there is a miss means that means 30% of the data will not be found in TLB. For this 30% of data you will access main memory. Okay, you will access main memory, and out of these 30% accesses in main memory, 20% of the time data is not found in the main memory. If data is, so there are two possibilities. Data is found in memory. Okay, if there is a hit in memory, then data is found in memory, right? That is 80% of the time. 80% of the data is found in the memory, but 20% of the time data is not found in memory. Data is not found in memory means there is a page fault. If there is a page fault, you will run the page fault service routine, and the page fault service routine time is also given. Now see the formula which I am making for this and understand how I am making the formula. So effective memory access time will be like this. So TLB access time given in this single level table, the memory access time is 5 microseconds and the page fault access time is 25 milliseconds. That means memory access time is given, that is 5 microseconds, and the TLB access time is not given, that will be, we will take 0, and page fault service time is given 25 milliseconds, and it is given that TLB hit ratio is 70%, that is 0.70. Okay, so first you will search the data into the TLB. So you will add TLB access time plus main memory, right? But if data is not found in TLB, that means 1 minus hit ratio of TLB, then there are two cases. One case is that the data will be found in the main memory, that is 20%, because if 20% of the time data is not found in memory, that means 80% of the time data is found in memory. So 80% of time you will access the page table from main memory, right? Then you will access the page table into the TLB. You will transfer this page table into TLB, then access the data from main memory. But 20% of the time, okay, 20% of the time data will not be found in the memory, so you have to run the page fault service time. Okay, you have to run the page fault service routine. Okay, 20% of the time you have to run the page fault service routine, right? So page fault service routine will simply load the page from hard disk to main memory, and then we'll update the page table, and then we'll restart the access. Okay, so into page fault service routine plus, then you will access the main memory, then you will access TLB, and then you will again access the memory. So the formula will become like this: hit ratio of TLB is 0.7, right? Access time of TLB is 0, memory access time is 5 microseconds. Let me convert this into the milliseconds. So microsecond to millisecond will be a smaller unit. Okay, so let's take this only microsecond. So 1 minus STLB will be 0.3 into 0.8. Hit ratio, access time of memory will be 5 microseconds plus 5 microseconds plus 0 for TLB access time, plus 0.2 into page fault service routine is time is 25 milliseconds. So we can convert this into microsecond, and this will become 25,000 microseconds, right? Plus memory access time, that is how much? 5 microseconds plus 5 microseconds plus 0. So this will be 0.5735, that is 733.5, and this will be 0.30 into 0.8 into 10. 0.8 into 10 will be 8, right, plus 0.2 into, so 25,000 plus 10, that will be 25,010. Okay, you can further solve this and you will get the answer. Okay, so the process is very simple. First you will search the data, first you will search the page number into the TLB. If the page number is found in the TLB, then you will convert that virtual address to physical address from the TLB, and then you will directly access the memory, right? So if the page number is found in the TLB, then you will access the TLB for the page number. Once you will get the frame number, you will go to the memory and you will access that frame number. If the frame number is not found in the TLB, if there is a miss, then you will access memory. Okay, and in the memory it is given that 80% of the time data is found and 20% of the time data is not found in the memory. So this will be your formula for this particular question. This is little bit complex. Do not worry if you are not understanding this, just you can simply like ignore this question, but you need to remember this formula. This formula is really important. ये formula आपको याद रखना चाहिए. Okay, you have to remember this formula. Following allocation is suffering from the external fragmentation of 60 kilobytes. The amount of memory that must be moved in order to get an efficient compacted memory in kilobytes is what? Okay, so you can see here there is a 60 kilobytes external fragmentation, right? We have this free partition of 20 kilobytes and we have 40 kilobytes of free partition. So we have two options, either we can move this partition up or we can move this partition down. So compaction means we will move this partition here. So moving this partition here will take how much? So you have to move how many bytes? 20 bytes and then 50 bytes. So these 20 bytes will be moved here and 50 bytes, or you can say these three partition will be moved up, right? इन तीन partition को आप move up कर दोगे और इसको यहाँ पर down कर दोगे. So you can see you have to make a movement of 50 plus 60 plus 20, that is you have to make a movement of 50 plus 60 plus 20 and plus 20 byte also. Okay, you will move this partition here. So first you will exchange this partition with this, then you will exchange this partition with this, then you will exchange this partition with this. So total partition movement will be 130 kilobytes, right? 50 plus 60 is 110 and 20 is 130. So according to compaction, you will move these three partition up. So this partition will be moved here. That means there will be a total movement of 130 kilobytes, right? Next question is, our virtual memory has a page size of 1 kilobytes. There are 8 pages and 4 frames. The associative memory page table contains the following entries. You are given a page table. In this page table, it is saying that the page number 6 is stored in the frame number 0. Okay, page number 1 is stored in the frame number 1. So page number 4 is stored in the frame number 2 and page number 0 stored in the frame number 3. Which of the following virtual addresses will cause the page fault? Okay, it is asking you, we are given some virtual addresses and then you have to find out which will cause the page fault. Page fault means which of these is not in memory. For example, page number 6 is in memory, page number 1 is also in memory, page number 4 is also memory, page number 0 is also in main memory. So first you have to calculate the page number from this. So page number, how you can calculate page number? Page number will be nothing but virtual address divided by page size. Okay, virtual address divided by page size and the seal value of this. So virtual address is given 4098 bytes and the size of the page is 1 kilowords. 1 kilowords means 1024 words, right? So you will get how much? So from this you will get 5. Okay, page number 5. So you can see page number 5 is not in memory. That means it is a page fault. Okay, it will be a page fault. So 5124, you will divide 5124 divided by page size, that is 1024 bytes. Okay, so this will give you page number. So 1024 into 5 will be 5120, right? That means this will be 5120 point something, it will be point something, so it will be page number 6. Okay, so it will be page number 6. When you will divide 5124 with 1024, okay, you will get 5120 and then 4, so it will be 5 point something. 5 point something, when you will take the seal value, it will be 6, right? So you are talking about page number 6, and page number 6 is already in the memory. That means it will not be a page fault. Okay, then virtual address is given 1022. So 1022 divided by 1024 will be 1. Okay, you will take the seal value of this, this will be 1, right? That means page number 1 is already in the memory. That means it will also not be a page fault. Okay, for 6144 you will get the virtual address 6144 divided by 1024. Okay, you will get, I think, 7. 1024 into 6 will be 6144. So you will get exactly 6. Okay, you will get exactly 6. So this will also not be a page fault, because page number 6 is already in the memory frame number 0. Okay, page number 6 is already in the frame number 0. So option will be the right answer. This will be a page fault. All these will not be page faults. Okay, so next we will solve this question, and in this given that there are 25 bits in the physical address. So we are given a physical address which is of 25 bits. Okay, physical address is of 25 bits. The physical memory is divided into 32 equal partitions. That means number of frames. Okay, we know that physical memory is divided into frames, and number of frames are given 32. Okay, so we have frame number and offset in this. From the number of frames we can find out the F field. Okay, so log base 2 number of frames is your F field. This F is a frame address, and frame address can be calculated from the number of frames. That will be log base 2 32, and log base 2 32 will be 5. Okay, that means frame number is of 5 bits, and offset field will be of 25 minus 5, that is 20 bits. If the total number of entries in the page table are 2 to the power 22, then how many bits are there in the logical address? Okay, this is asking about how many bits will be there in the logical address or virtual address. Okay, so virtual address is divided into page number and offset, right? Page number and offset. Offset field we have already calculated, that will be of 20 bits. Okay, virtual address, you have to calculate the length of the virtual address. So if you have to calculate the length of the virtual address, then you have to find out how many bits will be in P and how many bits will be in D. And P field we can find out from the number of pages. Okay, P field we can find out from the number of pages. P field is nothing but log base 2 number of pages. So number of pages are not given in the solution, right? Number of pages are not given, but one thing is given, that is number of total entries in the page table. And we already know that number of page table entries is equal to number of pages, right? That means number of pages are 2 to the power 22, right? So P field will be equals to log base 2 number of pages, that is 2 to the power 22. Log base 2 to the power 22 will be 22. That means P field will be of 22 bits. So the length of the virtual address is equals to 42 bits. Okay, length of the virtual address will be of 42 bits, right? I hope you are getting this. Now we have this quick question. I will stop here for 2 minutes, and I want you to solve this question. Okay, please try this question. So pick your pen and paper and try this question quickly. In this it is given that you have a byte addressable system, logical address space is 2 to the power 32 bytes. That means the size of the logical memory or size of virtual memory is given. Size of virtual memory. Okay, logical address space is nothing but the size of the logical memory, that is 2 to the power 30 bytes. Page size is given, that is 1 kilobyte. The total memory required for storing the page table is 2 megabytes. Okay, it is saying that the total size of the memory required for storing the page table is 2 megabytes. That means size of page table is given. Okay, size of page table is given, that is 2 megabytes. If each page table entry also contains 3 bits for bookkeeping, then then size of the physical memory in megabytes is what? You have to find out the size of main memory. Okay, so मैं आपको एक hint दे देता हूँ. You can find out the size of main memory from the physical address. Okay, size of physical address. From the size of physical address you can find out the size of physical memory, and physical address is frame and offset. Offset field आप यहाँ से find out कर सकते हो, right? So size of physical memory will be 2 to the power physical address, इतनी bytes. Okay, so try this question quickly. Okay, so what is the size? 2 to the power 23. Sri Lakshmi, Khushbu, Neelam, I am happy to see that you have tried. Very good. देख के मज़ा आ रहा है कि आप लोग सॉल्व कर रहे हो. Okay, so we know one thing. If you want to find out the size of the main memory, you should know what is the size of the physical address. And the size of the physical address you can easily find out. D field you can find out from the page size. Okay, so D field will be log base to page size. Okay, page size or frame size. And we are given that the page size is 1 kilobytes. 1 kilobyte means 2 to the power 10 bytes. That means D field will be of 10 bits. Okay, so D field will be of 10 bits. Now I need to find out frame number. Okay, how many bits are there in the frame number? So we have to find out. So we are given this virtual memory is 2 to the power 30 bytes. So we know that the virtual memory size is given. Okay, that is virtual address will be of 30 bits, right? Virtual address is nothing but log base to virtual memory size. Okay, virtual memory is 2 to the power 30 bytes. Log base to 2 to the power 30 means 30 bits. So virtual address will be of 30 bits. So that is divided into page number and offset, right? Page number and offset. Offset bit is R10 and number of pages will be, so page number will be of 20 bits, right? So we know that the size of the page table is number of page table entries into size of each entry. Okay, size of entry. and we know that size of page table is already given, that is 2 megabytes. Okay, 2 megabytes is the size of page table, and we know that number of page table entries is equal to number of pages. Okay, number of page table entries equals to number of pages, and number of pages are 2 to the power p, and p value we know that is 20 bits. So number of pages will be 2 to the power 20. So this will be 2 to the power 20 into size of entry. Now we find out the size of entry. Okay, size of entry will be, okay, size of entry will be 2 to the power 21. Okay, this will be 2 to the power 21. 2 megabytes means 2 to the power 21 divided by 2 to the power 20. You will get 2 bytes. Okay, size of entry is 2 bytes. Okay, size of entry is 2 bytes. So it is saying that in this entry of 2 bytes, okay, you in this entry, so we know that we have find out the size of the page table entry. Okay, this entry is of 2 bytes, or you can say 16 bits. Okay, the size of entry is 16 bit. In this entry we have the frame number, and we have the 3 more bits for bookkeeping. So 16 minus 3 is 13. That means frame number is of 13 bits. Okay, frame number is of 13 bits, right? So physical address becomes of 13 plus 10 is 23 bits. Physical address becomes of 23 bits. So size of main memory will be, size of main memory will be 2 to the power 23 bytes, and this will be 8 megabytes. So the answer for this question will be 8. Okay, if you can connect all the PCs together, then the question is really simple. The question is simply aptitude question. If you can connect all the dots together, the question is a simple okay, so if you join all the all dots together, you will get the answer together. Next question is very simple question. In this it is given that we have a 2-level paging scheme. Remember, this is 2-level paging. In case of 2-level paging, you have to access memory 2 times. Okay, you have to access memory 2 times to convert the virtual address to physical address, because you will have 2-level paging, right? So in this question it is given that the TLB access time is 10 nanoseconds. Okay, TLB access time is 10 nanoseconds, and the memory access time is 100 nanoseconds, right? What should be the TLB hit ratio if you have the effective memory access time of 150 nanoseconds, right? In case of multi-level paging, the formula for effective memory access time will be same what we have find out for the single level paging. There will be only one difference, बस एक छोटा सा difference होगा. Hit ratio of TLB, it will be same into TLB plus memory access time plus 1 minus hit ratio of TLB. If the page is not found in the TLB, then you will have to access memory 2 times to convert the virtual address to physical address. Then you will send the page number into the TLB, and then you will access the data from the main memory. That means there will be, in single level paging, here you will have only 2 times memory access. In 2-level paging, you will have 3 times memory access. In 3-level paging, you will have 4 times memory access, right? Effective memory access time is given, that is 150 nanoseconds. You have to find out the hit ratio. Okay, you have to find out the hit ratio. TLB access time is given 10, memory access time is given 100, plus this will be, you have to find out HTLB, you have to find out. Memory access time is given 100 into 3 is 300 plus 10. Okay, so the equation will become 110 hit ratio of TLB plus 310 minus 300 and hit ratio of TLB. Okay, so you can see this will become, so this will become 190, right? So 190 into hit ratio of TLB equals to this is 300, this is 310. 310 minus 150 will be, I think, 160, right? 160 plus 150 will be 310. So this will become hit ratio of TLB equals to 160 divided by 190. Okay, so this will be into 100. Whatever you will get the answer, you will get your answer. So what will be this? So we have done everything right? 110 TLB plus 310 minus 310. Okay, this will be 310 hit ratio of TLB. So this will be 310 minus 110, that means 200. Okay, this will be 200 and this will be 200. Okay, so this will be 4 4 ja 16, 4 5 ja 20, 5 20 ja 15, and this will be 80%. So heat ratio will be 80%. Okay, so I did a mistake here. मैंने यहाँ पे एक छोटी सी गलती करी थी. 310 इंटू हीट रेशियो ऑफ TLP विल बी 310. वो मैंने मिस्टेक सही कर दी है. 310 हीट रेशियो ऑफ TLP माइनस 110 विल बी 200 हीट रेशियो ऑफ TLP. Right, so the answer will be 80%. So this is the last question for today. After this I will close the class and you will solve the remaining question. In this question, in a computer system, size of the logical address space and the physical address space is 32 megabytes. It is saying that size of virtual memory or logical memory is equals to 32 megabytes, right? And the size of the physical memory, or you can say size of the main memory or RAM, is 256 kilobytes. If the page size is 4 kilobytes, okay, we know that page size is equals to frame size, that is 4 kilobytes. Then the number of pages in the system is what? This is very simple question. Number of pages in virtual memory is equals to size of virtual memory divided by page size, and this will be virtual memory size is given 32 megabytes and page size is given 4 kilobytes. Okay, so this is 2 to the power 25 bytes and this is 2 to the power 12 bytes. I will suggest कि आपको पेजिंग के सारे क्वेश्चन 2 की पावर्स में करने चाहिए. Everything should be converted to the power of 2. फिर आपको आसान पड़ेगा. This will become 2 to the power 13 number of pages. Okay, number of pages will be 2 to the power 13. You can make the address division also. Virtual address will be of 25 bits because the size of the memory is 32 megabytes. This will be 2 to the power 25 bytes. Log base 2 to the power 25 will be 25, right? So offset and page number. Offset field will be of how much? 12 bits. Okay, and the remaining is 13 bits for the page number. Like this you can find out the physical address format also. Physical address format will be frame number and offset. Physical address will be of 18 bits. Out of the 18 bits, 12 bits are for the offset and 6 bit will be of frame number. Okay, from this you can find out the number of frames. Number of frames is nothing but 2 to the power f. So number of frames will be 2 to the power 6, that is 64. Okay, आप ऐसे भी कर सकते हो. So number of frames is also equal to main memory size divided by frame size. So main memory size is given, that is 256 kilobytes divided by frame size is given, that is 4 kilobytes. यहाँ से भी आपका सेम ही आएगा, that will be 2 to the power 18 divided by 2 to the power 12, that is equals to 6. Okay, 2 to the power 6, that is 64. So they are asking only number of pages. Number of pages are nothing but 2 to the power 13, or you can say 8 into 1024. This will be 8124. Okay, so I am giving you remaining question. Try to solve the remaining questions yourself. So I have something at 9 p.m. I have to go now. Okay, so thank you everyone for attending the class. जो भी आपके डाउट्स हैं, मुझे पता है कि बहुत सारे बच्चों के डाउट्स होंगे. बहुत सारे बच्चे स्पीड पे बहुत सारे बच्चे जो है वो स्पीड के साथ में मैच नहीं कर पाए होंगे. तो आप अपने सब डाउट्स कलेक्ट करो और ग्रुप पे पोस्ट करो. अगली क्लास में मैं आपको सारे डाउट्स क्लियर करूँगा आपके, अगर कोई भी डाउट्स है पेजिंग में. इन द नेक्स्ट क्लास वी विल डिस्कस फाइल मैनेजमेंट एंड डिस्क मैनेजमेंट. Okay, so we will have one more class of operating system. In that we will complete the operating system and then we will start computer architecture. Okay, so have a good night. Thank you.